Hello. In this third section, we are going to discuss the LRFD method, or the load reduction factor design method. And this is what is presented in the ASHTO 2012 specifications that have been attached throughout this section and will be attached throughout this course. Equation 3.8.1.1-1 is for the wind speed at height z. And this is within the section 3.8 that discusses wind loads. To calculate wind speed at height z, we first need to find our friction velocity, V0, our 30-foot wind velocity, V30, our base wind velocity, VB, our height, and our friction length, Z0. In this case, V30 is equal to VB, or our base, at 100 miles per hour. And then we'll use table 3.8.1.1-1 in the open category, which is the worst case scenario, to get our numbers for V0 and Z0, 8.2 and 0.23. We'll assume the same height as the previous section, about 50 feet. And that gives us a VDZ, or our design velocity at 50 feet, to be about 110.3 miles per hour. Moving on to find our pressure, similar to before, with our Q and P, we'll find PD, our design wind pressure, KSF, based off PB, our base wind pressure, which we'll take from table 3.8.1.2.1-1 under the category of a large surface, which gives PB a value of 0.04. Sorry about that. KSF. And we'll use what we've calculated previously to calculate a value for PD, which at 50 feet, we should get that value to be approximately 0.048 KSF, which we then can calculate into kilonewtons per meter, which should be about 0.94 kilonewtons per meter, based on the geometry we discussed in the previous section for the equivalent amount of area we have, solid over gross area. In addition to our horizontal wind pressure, we also can use the LRFD document to find a vertical wind pressure, which is just specified as 0.02 KSF in section 3.8.2. And this is important because it creates a torsion, because it is mentioned in the code that this load applies, this line load. So think about this load applying per meter in this direction into the page and out of the page. And that load at the windward quarter point is going to create some sort of torsional force on the walkway. And what we discussed the previous two sections was that the thesis that is linked in this page went through the calculations and determined that any bridge less than 80 meters and with a 5% design sag is not at risk for torsional instability. So we won't go into that process now because it's more complex. But if you were interested, you can read the thesis. And coming soon later in this course, we're going to discuss lateral stability, and we'll discuss actually how we would take these loads and figure out if they are going to overcome the dead load here, and what we need to do to mitigate this. The last thing I want to discuss with the LRFD method, which is really just for learning purposes here, it is the future. It is what some more of the complex calculations we'll use, because the LRFD method allows for higher loads but more reductions, depending on the use, versus the ASD, which is which can be allowable stress design, which can be more stagnant, which can be more, you have one reduction, and if your stresses are higher than what's allowed, then it's not going to pass, where the LRFD, depending on the situation, can allow for a more efficient design. But that was a digression. And the last thing I want to discuss is the load combinations, which are important for the load reduction factor design method. And the two combinations we're concerned about in this case are known as the strength 3 and service 1 calculation, which you can find in the document. And here you notice there's value of 1.4 wind load and 0.3 wind load. What's important here is that 1.4 wind load brings that 100 per hour wind velocity up to a ultimate velocity from its design. And that is going to represent the potential for, or the probability for, even stronger winds. And that 0.3 is bringing down the 100 miles per hour to what mentions in the code 55 mile per hour wind, which is the assumed amount that people would still be potentially using the bridge. So it needs to be still serviceable with 55 mile per hour winds. Whereas at 1.4 times 100 or 140 mile per hour winds, it doesn't necessarily need to fit the serviceability requirements, but it needs to fit the strength requirements. People might not be on it, but the bridge can't fail; it can't flip over. So that's why these values are relevant.